So let us start the live session. I hope so that I am audible. I guess so I'm audible, guys. Hello and welcome back to Coders Arcade, guys. This is Ashank David, and in today's live session, this is going to be our live session number 27. In today's live session, we will continue from our previous live session that was about red and black tree. So today we will try to finish up the red and black tree concept, and today I have brought something important for you. I have some notes. The notes I will give the link in the description as soon as I end of this session. You will understand. All those notes will be given in the description below later on. Today I will be talking to you guys about red and black tree, and we will be finishing up this concept. So let us start, guys. Okay, before I start with this, just testing if I am audible. Yeah, I am audible, and I hope so that my screen is also visible. Right, the focus is also good. I am alone doing the camera thing, guys, so make sure that if you have any doubts or problem, please let me know before only. This way I will be able to clear that off. Okay, alright, let us start. Now before I start with this, guys, I would like to request you people to please like, share and subscribe, and don't forget to press the bell icon also, so that you won't miss any future update. Apart from that, please do share this live stream to those people who are really interested in learning DSA for free, and they are looking for a course like this. So please do share this live stream as much as possible, so this live stream can reach those kind of people who really know, who really needs it. Alright, guys, let us start. So in the last class we have talked about, till now red and black tree. So what exactly was this red and black tree? So here the concept was red and black tree. Okay, so this was the concept, and what we have understood in yesterday's class till now, what we have understood till now about this red and black tree, guys, it was that what we have understood till now is that a red and black tree, it is a self balancing tree. It is a self balancing tree. We have understood this really well. Okay. Also, how does it balance itself? It balances itself using the color rule. Okay, using the color rule. What is that color rule? That color rule has says that a node can only be either red or black. Either a node can be red or black. I hope so that this is very much clear. Okay. Now after that, depends upon what to do, what happens in this case. Okay, guys, so let us start. So in this case, generally when we are doing any type of insertion, we know this that a red and black tree is a binary search tree. It is what? It is a binary search tree, BST. We know this very well. I hope so you are getting my point. So the insertion what we will be doing inside this BST, the insertion what we will be doing in the red and black tree will be taken as the insertion as binary search tree. Guys, we have already done binary search tree last week. If you have not watched that video yet, I would like to give you a comment on that please do watch that video, because that's a very important video. And BST is a concept which will generally be 100% asked in interview, no matter in whatever interview you go. Alright, guys. So that is the reason why you should know about what is binary search tree. If you are new to this channel, please go ahead and watch our BST video. Alright guys, let's continue. So here this is red and black tree is a what? It is a BST, binary search tree. That means let us say, and always we have understood that root is always black. Root is always black, and a red node. So I'll write the rules for that right here. So I'll say there are some rules to this. There are some rules to this, guys. So let us talk about that. So there are some rules. So what are those rules? Basic rules. It's not all of them, but it is here. Pretty much it is there. So in this case, the very first one is that the root is black. The root is black. The root is black. Then root. Okay, black nodes can have black subnodes, or you can call them as child nodes. Understood this? Then number 3, a red node cannot have red child node. So a red cannot have red. So if I am saying that a black has a black child, then this is fine. But if I say that a red will have a red child, this is not fine. I hope so that this is very much clear. So the nodes are here just painted. Here the nodes are just painted, and based off of the colors we talk about the tree if it is balanced or not. Hope so that this is very much clear. So now I have one PDF to show you, where today I will be explaining you how it works. Now this PDF is way too bright, so guys, 1 minute, let me set up the camera for you. Just a minute guys, I need to bring down this, and this device will be much more clear. I hope so that this is very much clear. Okay, am I visible? Little bit, yeah, or yeah, I hope so that everything is fine guys. Okay, focus on to the PDF now. Okay, focus on to the PDF, not me. Okay, alright. So here we see that okay, let me just increase the font size. Let me just zoom in here. Okay, so we understood that a red and black tree is a self-balancing BST where every node has the following rules. Let us talk about that rules. So these are some of the very important rules. Number 1, root. Every node has a color of either red and black. Root of the tree, we know this that it is a red and black tree, so either the color can be red or the color can be black. Okay, apart from that, root of the tree is always black. Correct? Every leaf node is a null node. So every single leaf node, what you will see here is gonna be the null node and is painted as black. Okay, then both children and red nodes are black. Both children of red nodes are black. A red node cannot have both children as red, or not even a single one side, either left or right. It cannot have any red child. If there is a red node, this is a very important point guys. If the node is red, then that red node is not going to have any red child. It can have black child, but it cannot have a red child. Hope so that this is very much clear. Now every path from a node including the root to any of its descendant. Now what it says, every path from a node including the root, okay, including the root to any of its descendants node have the same number of black nodes. It will have the same number of black nodes. It doesn't matter how many descendants are there. So in every branch it is going to be the same. No root to leaf path connects two consecutive red nodes. Here in this case, no root to leaf path. So whenever in this case, while you are traversing from the root to any of the depth of the nodes, none of the nodes cannot be of the same color. That means we are talking about the red nodes here. When the nodes are red, those red nodes cannot be taken into the consideration. So red below red cannot be possible. Well, I hope so that this is very much clear. Alright guys. Then no root to leaf path contains two consecutive red nodes. This is done. For each node x, all path from x to descendant leaves contains number of black nodes the same number of black nodes will be consisted in this case. Okay guys, contains the same number of black nodes, not counting x. The number of the black height is the node x, denoted by BH. Hope so that this is very much clear guys. So these are some of the basic rules that everyone should know about it. And guys, see, this is how a red and black tree it looks like. This is how it looks like guys. So in this case, you see that the root is black. The root is black. The left and the right side is one black and one red. No problem here guys. No problem in this case. A black node can have black children or even a red children, but a red node cannot have a red children directly. The red node can have any black children, but it cannot have the same red children guys. I hope so that this is very much clear. So this is how the node it looks like. Clear guys? And all the leaf nodes are always null. All the leaf nodes are always null. So you see this part is always null. I hope so that this is very much clear. Okay, this is the tree guys. Okay, now in this case let us see the need for the red and black tree. Okay, most of the binary search tree takes the operation O, do the operations in O of h. Most of the binary search tree operations take O of h time complexity. Here we are talking about time complexity where h is the height. What is this h? H is the height of the tree in the depth. Height of the tree in the depth. So that is the height of the tree in the depth. And if the binary search tree becomes skewed, then height of the tree will become equal to total number of nodes as n, and the time complexity will increase n. So basically every single time, because of this property, every single time whenever we need to do insertion or any operation, we need to maintain the property of binary search tree. And we have already understood this previously in long back in the last week. So guys, so to make the time complexity low, we should balance the binary tree, and after each insertion and deletion, this ensures that the height of h of the tree as log n and time complexity as O log n, big O of log n. I have explained to you time complexity in 2-3 classes before. Okay guys, so please make sure that you make a note of it. All the content is there in our previous videos. I hope so that this is very much clear. So the height of the red and black tree is always log n. I hope so that this is very much clear to all of you. Okay guys, I hope so that it is visible. You guys are not saying anything, so I'm gonna increase a little bit of brightness here. Hope so that this is very much clear. If you have any problems or doubts guys, please do let me know in the comment section below, or in the chat. I can see the chat is live. Okay, other properties. See, here in the red and black tree, the height h has the height. Okay, this is just the height formula, everyone knows about it. Anyways, I'll put the link of the notes here. in the description below. So you will get it. What I'm trying to say here is we just need to understand how it works. Okay guys. So now guys, when the insertion happens, there are two things that the red and black tree uses to balance itself. And what are those two things? Number one, as it is given, recoloring and rotation. Recoloring and rotation, these are the two very important concepts. Now the trick here in the red and black tree is to understand when to recolor and when to rotate. Okay, so in the rotation part, I'll tell you how it works. Okay, we try recoloring first. If recoloring doesn't work, then we go for the rotation. Following is the detailed algorithm. The algorithm has mainly two cases depending upon. Okay, so what are those two cases? The cases are that if the uncle is black and red. So see, if the uncle is red, the grandparent must have been black. Change the color of the parent and the uncle as black. That means in these type of cases where you see that here the grandparent is black, but there are two red children. Okay guys, I hope so that this is very much clear. Now this is okay when you don't insert anything, but when you insert anything and if the red comes below red, then the violation happens. And when this violation happens, what happens is that you need to change the color of the parent and the child. Okay, parent and the grandparent basically. So in this case, P and U will become black and G will become from black to red. This is what you call as recoloring or reshuffling the colors of the red and black tree. I hope so that this is very much clear. Okay, now the screen is much more visible. Okay guys, I hope so that this is very much clear. Okay, now so now so in this case the violation has been happening here, right, in this case in T1, T2, T3, then only we are changing the color. Okay, and speaking of uncle being red, what is this uncle? So let me just tell you here, we use these kind of notations in order to understand the different nodes here. Okay, so in this case, who is what? We need to understand that. So guys, generally this is what? It is the grandparent. This is the grandparent. This is the parent. And this is parent's cousin, who is the uncle of this child. I hope so that this is very much clear. Oh my god, green is not visible at all. Let me just switch it back to maybe orange. Orange is visible? Yes, orange is absolutely visible. So what is this G? G is the grandparent. P is the parent. And U is the uncle. Because uncle and parent are both what? The brothers of the grandparent G. Understood? And here this X is the child. So child's uncle is U, while X uncle's is U. And we know this, that this is the violation happening right over here. When this situation is caught, when you see the uncle is red, see, the thing is that very simple. When you do recoloring, we do recoloring when we see the violation being happening. Basic violation is that red below red cannot be possible. So this is red below red. Now when this violation happens, you check for this uncle. Is uncle red? Yes, the uncle is red. If the uncle is red, then you do recoloring. Recoloring means now the parents will be black, uncle will be black, and grandparent will become red. So that red color will be swapped with the grandparent for both parent and uncle, and this will become something like this. Now you see that we can say that this tree is balanced. Because of this rule, the tree is balanced. We are not saying that this tree is not balanced. This tree is not balanced. I know it is balanced. By looking at it, it is balanced. But the thing is that according to the rule of red and black tree, it does not say that it is balanced. Why? Because this is how it works. The red and black tree does not have the concept of calculating the heights of the trees using -1 or 1, like how we did it in AVL trees, Adelson-Welskis and Landis tree. But in this case, what happens is that here in the red and black tree, we are trying to actually depend upon the rules which are made for red and the black color itself. Hope so that this is very much clear. So, whenever the violation is made and you see that the parent and uncle are red, you just recolor the parent and uncle and the grandparent and the issue is resolved. And this is how you do this basic recoloring stuff in the case. Okay guys, what if the uncle is black? If the uncle is black, in the previous case, in just now this case, we saw that the parent was red, uncle was red. What if this is this guy? What if the uncle in this case, what if the uncle in this case is black itself? If the uncle itself is black, which means if the uncle becomes black, which means now you cannot do recoloring. Now you cannot do recoloring, is not allowed. Okay. So in that case, what you will do? There are 4 cases, guys. There are 4 cases that you will see right here. The 4 cases are when the left case, left case, the left child of G, the P is the left child of G and X is the left child of P. Meaning the tree looks like this, black, then the parent is red, and then the left is also red. This is our child. The child is also red, and the uncle on the other hand is black. I hope so that this is very much clear, guys. Again, let us draw it. Here we will draw it. Grandparent and uncle are black, but the parent is red and the child is on the left hand side of the left hand side. That means this side, left hand side of the parent is red. Violation has happened there, guys. Violation has happened here. So in this case, you see that we will do rotate. Understood my point? So in this case, we will do the rotate. Okay. If then what if the left right case is there? Left right case means the parent is left and the child is also shifted from here to now it is right here for you, and I am going to rub this off from this side. So this is the case. When you see that this is null, okay, this is null, this side is null, but the child is on the left right. This is left right, that is root, that is left, this is right. So this is left right case when P is on the left hand side and the child is on the right hand side of the P. Understood my point? Like this is one of the case. So here also we do rotation. Then we have right case. That means the mirror case of I means mirror case of the previous one. That means now this time the grandparent is black and the left parent is also black. Left uncle is black in this case, but this is the root, the uncle is black. Now we are saying that okay, so we are saying that the this one, okay, the right side the parent is black, the right side the parent is red, and this side, this is right means not this side but this side, the child is present. In that case, this is the mirror. So here the violation has been made, correct? This is the violation, and for that reason also we will do again rotation. Okay, another case could be possible for this, where the child is kept at this position. I hope that this is very much clear. So this is how the violations are gonna be kept when the uncle is black. Okay guys, I hope so that this is very much clear. Okay, so now these are the 4 cases. So all 4 cases we will see when the uncle is black. So when the uncle is black and the left case is there, when the left case is there, uncle is black in this case. So what we will do, we will rotate it. So grandparent will become and come at the place of uncle, and uncle will be shifted down the line, and then the parent will become the root and the child will become the child again for the below the parent again. So in this case, this is called as right rotation. Right rotation. I hope so that this is very much clear to all of you. Basic thing, and you see that now the colors are balanced and the tree is automatically balanced, guys. What if the left right case happens? This was the first case, left. Now this is the left right case, where you see that the grandparent is black, parent is red, now child is on the right hand side of the parent, which is red, and uncle is black. In this case, we need to do left rotate and then left rotate in this case. So this node will become the parent, and parent will come down the x. In this case, you see x has become parent and parent has come down to x, and then we will do left rotate in this case. Okay. So the above case will be done, and this way what will happen, grandparent will go down, uncle will go down the line, and then x will become the root in this case. This is another thing. Hariharan Panicker, hi Hariharan. My camera went off, I need to just press the button and we are back. Okay guys, hope so that this is very much clear to everyone, guys. Okay, next up, what happens when the uncle is black and it is right case? Then it is very simple. The mirror case of the first case, we will be doing the left right rotation. Okay guys, then comes left rotation in that case, and then comes the right left case, where you see the child is on the left hand side of the right parent in this case, where again we will do the same thing. This will come up and then we will make it as the root, and this is how it will work, guys. I hope so that these 4 cases are absolutely clear, guys. So in this case, this is how it is done. Now no need of this part, but I will give the notes in the description below, guys. Now let us go ahead and watch and understand the code, how the code is being made. Now let me just increase the brightness a little bit so that it is visible too much. Okay, this is much better actually. Okay, hope so that it is clear. I am also visible. Absolutely. So guys, here we are gonna use enums in C++ now. What is enum? So let us talk about enums. So here enums are what? Something like a class which is very constant. In enums, the values or whatever I am going to write will never change in this case. So you see here, we know that the red and black color are only being used. So I took a enum of it. Okay. Starting with this Q is for BST. Okay, binary search tree, for that reason. Okay guys. Hope so that this is very much clear. Okay. Now in this case, what is happening here is that we started by creating the node class. It is very prominent, we know this. Now in the node class, what is happening here is that we have taken the data, we have taken the color, we have taken the left and right, and we have taken the parent in this case, to just keep a track of who is the parent and what is the color of the parent. Based off of the color of the parent, we will see that if the if the color of the current node or the current inserted node and the parent node is red or not. Understand my point? So, every time we enter it, we will mark it. Okay. Now, in the constructor of the node class, here we said that this of data equals to data, this of color equals to red. As soon as in the constructor itself we have we have implemented the concept of red. Any node which is inserted, newly inserted, as we have understood and we have read this in the rule, every node which is going to be inserted is going to be always red, guys. I hope so that this is very much clear to all of you. Okay, guys. So, that is the case here, guys. Okay. Then we have left and then we have right, then we have parent. These are all just the other attributes in this case. Okay. Then we have the private section of the red and black tree class, and here we have written the logic of left rotate. Left rotate is exactly the same as how we have written in the ABL tree. Just the thing is that you can see how did we do it. We have taken the right node and we have taken we have asked the right node to shift on the right hand side. So, I said node right will node go to its right, nodes right again. So, right will come at the right and nodes right position will come at right, the left node will take nodes right position will be taken by nodes right's left. It's a little bit confusing though, but this is the logic. I hope so you will get it in a moment as soon as you see the code. So, pause this video. If you are watching the recording, then pause this video. For live session people, this is how it is done. Okay. So, if you, later on when you will see the later on again, anyways you have to see the recording. So, at that time you pause it and then check for this. Okay, guys. Apart from this, if the node's right is null pointer, which means in this case you will check the parent. So, in this case node right of parent is equals to node itself. Understand the point? Other than that, node's right of parent will become the node's parent itself. This is going to be the left right position. So, the whole thing is there. So, just the left rotate we have written, and in the left rotate we have written the concept of left right and right left also in both the cases. Okay, and in the right rotation we will do the vice versa in this case. Hope so that this is very much clear to all of you guys. Okay, so this is how it is gonna be done. The same thing is gonna be done for the right rotate, where we have just changed the left to right and right to left. Understood my point? That is the case. The rest of the code is always the same. Okay, after the insertion, when the violation happens, for example, red below red comes, then what to do? This is the function for it. So, node the parent will, whatever the parent is, initially it is null and the grandparent we do not know. Okay, so we will check while the node is not equals to root and the node color is red and the node parent color is also red, then the violation is found. Okay, in that case keep on traveling, parent keep on traveling and grandparent you will also keep on traveling behind the parent. Okay, so in this case what happens is that we found the element. Once we found that element, we will check if the if the parent is equals to the grandparents of left. If the parent is equals to the grandparent of left, then the uncle we will check if it is on the grandparent of the right in this case. And if then here's the cases comes. If the case one is that if the uncle is red, just recoloring it will be fine in this case, as we have understood this already. So, the grandparent's color is going to be red, the parent's color is going to be black, uncle's color is going to be black, and the node will become the grandparent itself. Otherwise, if the node is on the right and the node is right child and left rotate we want to do, we will just call the left rotate right over here if the child's parent is equals to right in this case. Understood my point? I hope so that this is very much clear. For the other cases, right rotation, when the node is on the left child, then we will do right rotate. Okay. And then the parent is on the left side. So, these are the 4 cases that we have written right there, one by one. And that is all, guys, about this concept. I will give the link of the code in the description below, and I will pin up this code in the comment section below. So, you go and read this code first, try to understand what I have said just now, rewatch the logic, and you will get the correct answer. You will understand how it works, guys. I hope so that this is very much clear. Code implementation is very easy because we are doing the same thing what we were doing in an ABL tree. We are doing the same exact thing here also, just the colors are taken in the consideration. Guys, this is how you will do red and black trees. So those people, now this is a very advanced concept, guys. So if you have any problem understanding this, probably you have not watched our previous live session. So please go ahead and watch our previous live session, guys. I hope so that this is very much clear to all of you. So we have done binary trees, we have done binary search trees, we have done AVL trees, we have done splay trees, we have done red and black trees, guys. I hope so that everything is very much clear. I'll give the link of the PDF also in the description below, and I'll tell you about all the concepts right there. Any other doubts, you please may ask in the chat window right here. I can see your chats, guys. If you want any answer or if you have any doubts, please do let me know in the chat window here. I can see the chat window. Tomorrow, guys, I'll check for what topics we can do tomorrow, because concept is almost over, and I don't think so that I guess a tree is enough. This much of trees is done enough. We have done a lot of different kinds of tree. Okay. Apart from that, we have a lot of concepts left yet. We have to do heaps. Heaps are very important. We need to understand about how heaps they work. Okay. Then we need to understand how priority queues work. Next concept I am going to take on priority queues or heaps, guys. Actually priority queues first, because heaps are a type of a priority queue only. So in tomorrow's class I will start from priority queue, guys. I hope so that this is very much clear. Till now we have finished up stacks, stack implementation of array, stack implementation of linked list, queues, queues implementation of arrays, queue implementation of linked list. We have understood about the concept of linked list properly, singly linked list, doubly linked list. We have understood the concept of trees properly. We have finished up binary trees, we have finished up binary search trees, split trees, red and black tree, AVL tree, Adelson Elkis tree. We have finished up all of this till now. So if you have missed any other concept, there are other videos also which I have created the videos onto other concepts, other topics. Please go ahead and watch that, and you will understand it in a better way, guys. Apart from this, I hope so that this is very much clear. If you have any doubts, please do let me know in the comment section below. And for the tomorrow's class, it is going to be the same timing, 7 o'clock in the evening. Tomorrow I am going to start with the priority queue, guys. Tomorrow I am going to start with the priority queue, guys. Alright, guys, I hope so that this is very much clear. Okay, so well, that's it, guys. I would like to request you people to please like, share and subscribe to our channel, and don't forget to press the bell icon also, so that you won't miss any future updates, guys. Apart from this, thank you so much for watching till the end of this video, guys. This is the end. I hope so that this is very much clear. Any doubts or any thing to discuss, please follow us on our Telegram channel. We have already created a community on Telegram channel. So if you are not connected to that community, please do get connected with our community. And my camera went off and my camera came back, right, like that. Please do, I hope so that I am visible. Please do join our Telegram community. There we keep on posting our latest updates on any video that we are coming up with, or anything which is thing. So in this case, we are going to talk about internships very soon. We are going to talk about mock interviews also soon, and also we are going to talk about other concepts related to placements as well. So I'm trying still my level best in order to get more companies to for the placements, guys. So if you have any issues or any problem, please do connect with us, and we will try to solve the problems. The link is already given in the description for the Telegram below. Join that community, as many as possible, for the latest updates for jobs, for placements, for interviews, for mock interview sessions, for any other doubt or for any other updates on DSA. We are also doing crash course for DSA, guys. So if you are interested in joining my DSA course, offline or online, I am doing that also. The number is given in the description below, guys. So please go ahead and call us, or the number is also given in the channel's about section, where you can find our number as well. So if you think that this course is stretching a little bit long, because this is a free YouTube live session. Every day we are just coming one day, sorry, every day we are just coming 1 hour. It is not enough for us to follow all the concepts, but I am trying my best to complete it as much as possible, guys. But I hope so that you guys are enjoying this session, and on the little journey of DSA, of a placement series, we will finish up our stuff. Well, I hope so. That's all for today's class, guys. No doubts, we will continue the class tomorrow. Tomorrow we are going to start with a new concept, guys, for priority queues, and we will understand it really nicely. That's all for this session, guys. Thank you for watching. I'll see you guys tomorrow. This is Ashang David signing off. I will see you tomorrow. Till then, take care and happy learning, and don't forget to like, share and subscribe. Well, that's all, guys. I'll be closing the live session, and yep, take care, guys. Tomorrow 7 o'clock at the same time, you will see the scheduling in the morning.